So we talked about k-means, and we saw when k-means works or doesn't work, and we saw also that when the data is very high dimensional, k-means kinds of breaks down. But how high dimension is high dimension, and can we define it without just looking at the dimension of the data? So this leads us to this idea of intrinsic dimension. And the intrinsic dimension is basically the relationship. So is basically a relationship between two dimensions. So dimension is something like degrees of freedom or number of variables. And what you have here is a piston that is connected to a rotating rod and is moving in and out. And if we look at the image is pretty high dimensional, but the piston movement is really defined by just one angle that is here. So the extrinsic dimension is 600 to 400, 600 times 400 pixels, pretty high. But the intrinsic dimension is really just one, right? Because there's just one parameter that defines the state of the system. So we've seen this already before, right? We talked a few videos ago, we talked about the principal component analysis. And it is a method that if the distribution of the data is dominated by the largest d eigenvalues, then the set has, in a sense, intrinsic dimension d. We only care about these d dimensions, and the others are too small to, we can neglect them. Okay? So this is good when we can do this using linear algebra. Basically, we're just saying that the data is close to a hyperplane. But what can we do if the data that we're doing is not on a hyperplane? It's not the affine data set. What can we do then if we want to find whether the data is lower dimension? So here is the basic idea. We suppose that we have our data set, and it's uniformly distributed over some domain. This is not essential. It's just something to make us think about a simpler, concrete case. And we partition this data set into n cells. Okay, so each cell contains a neighborhood of the points. And we define the diameter of the partition to be the maximal distance between 2 points that belong to the same cell. Okay, so we're looking basically for a partition such that all of the cells have small diameter, and on the other hand, that we just have n cells. So, of course, as we allow n to increase, then epsilon, the diameter, would decrease. But at what rate? That's the critical question. So if we have different dimension sets, we'll see that epsilon decreases in different rates. So to do that, let's look first at a few simple examples. So the first one is a line segment. We have here a line going from 0 to 1. I'll have to stop here and set my...
All right, cut.
Yeah. Because...
Are we starting from the beginning? Or are we
No, just from this place, yeah.
Okay, and action.
So for the first example, let's look at the line segment. So here we have a line segment going from 0 to 1, and we partitioned it into 2 cells, so n is equal to 2, and the diameter of each cell is 1/2. What if we partition it into 4 cells? Then clearly the diameter will be 1/4. And if we go to 8 cells, it'll be 1/8, and to 16 cells, it would be 1/16. So the pattern is pretty clear. Epsilon is equal to 1/n. Okay? So that is what we get for a line segment. Second example, let's look at the two-dimensional set. So here we have a square from 0, 1 to 0, 1 horizontally and vertically. And we're partitioning it into 4. And there we get that the diameter of each of the cells, including the diameter of everything, is 1/√2. what if we want to decrease that? So let's take 16 cells. Now we have 1 over 2 times square root of 2. And if we increase that again to 64, we get 1 over 4 times square root of 2. So as you see here, the diameter decreases slowly, more slowly, because it is two-dimensional. And so what we have as a general rule is that the number of cells behaves like 2 divided by epsilon squared. Okay, so here it's epsilon squared. Let's look at 3 dimensions. So here we have a cube, and the diameter of the cube is square root of 3. If we divide the cube into 3 by 3 by 3, we get 27 cells, and the diameter is square root of 3 divided by 3. And if we divide each side by 5, then we get epsilon equal to square root of 3 over 5. So the general formula here is n is equal to 3 times 3 square root of 3 divided by epsilon to the third. Okay, so you see the pattern where the exponent of the epsilon corresponds to the dimension here of the set. So we can think about this as a general dependence of the number of elements on diameter. We have epsilon, which is the max diameter, and n, which is the number of cells, and d, which is the dimension of the space. And then the general formula is that n is equal some constant, we don't really care about this constant, divided by epsilon to the d. Okay? Or alternatively, if I take log on both sides, I get log n is equal to log c plus d log 1 over epsilon. We saw that for a segment and a square and a cube, we got particular types of relationships. We can summarize these relationships in the following way. If epsilon is the diameter and n is the number of cells and d is the dimension of the space, then the general formula is that n is equal to c over epsilon to the d, where c is some constant. We don't really care about that. But if we take the log of both sides, we get that log n is equal to log c plus d times log 1 over epsilon. And now we have an interesting, basically affine or linear relationship between log n and log 1 over epsilon. So that is something that we saw for the 3 cases of 1 and 2 and 3 dimensions. But we can actually reverse the idea and basically say, okay, if we get a general set, then we will define the dimension in this way. So that's what we can do. We can use this last relationship between n and epsilon to basically estimate what is the dimension d. Okay, so let's see how this works on a slightly more complicated example. So suppose we have this data set. All of the black points are data points. And we have like a region here that we have data points in, and this line that we also have data points. And on an intuitive level, we can say that this is a two-dimensional thing, and that this line is a one-dimensional thing. So let's see if the math agrees with us. So we do a partitioning of the space, as before, into finer and finer squares, and then we relate how many squares we have that touch the line, how many that touch the blob, and how many that don't touch anything. Okay, so here what we have is when the size is 1/4, there is 7 things that touch the line, 6 things that touch the blob, and the total is 13. When we go to the next slide, we see that the line now touches 30 and the blob touches 12, total for 42. So line touches significantly more than the blob. But now that we're looking at 1/16, we see that the number of squares that the blob touches is very close to the number of squares that the line touches. If we go even further, the relationship reverses, right? So now we have more squares touching the blob and fewer squares touching the line. If we go even further, we see that there is significantly more squares touching the blob and fewer squares touching the line. So now we're going to apply our formula, log n is equal to log c plus d log 1 over epsilon, to estimate d. Okay? So what we basically do is we take two scales, n1 with its radius epsilon 1 and n2 with the radius epsilon 2, and then we basically apply this formula to both to get at this thing. So we have that the log of the ratio of the n's is d times the log of the ratio of the epsilons. And if we rearrange this, we get that d is equal to log n minus log n2 minus log n1 divided by log epsilon 1 minus log epsilon 2. And that can be our estimate of the dimension. So again, let's see how that works. So here we have the points that we measured. So both for all the squares that touch the data set, that touch the line is the orange, and the ones that touch the blob is the green. And we plot all of these points. And moreover, we plot them on a log-log scale, right? So when we plot them on a log-log scale, then these curves are basically, they look very much like straight lines. Okay, so we can estimate what they are using the slope from the first point to the last point. Okay, so here's what we're doing. And the idea is that the deeper the decline, the lower the dimension. Okay, so let's see this in action. We are measuring the difference in epsilons between the two extremes. So that's log 10 of epsilon 1, log 10 of epsilon 4, equal to 0.9. We can use log on any base as long as we're consistently using the same base everywhere. And then for the horizontal, we're seeing that the blob has a difference between the log n4 and log n1 of 1.7. The line has 0.99. And what we get when we plug this into the ratios, we get approximately what we expected. So we get for the line, the dimension is 1.1, which is close to 1. And for the blob, we get 1.89, that is close to 2. So the significant thing about this is that we defined dimension in a way that is completely separate from our perception. Okay, it's just a ratio of how distances shrink and the number of cells grows. So to summarize, the relationship between diameter and the number of cells, when you plot it on a log-log scale, defines the dimension of a data set. So we'll continue with some more examples in the next video. See you then.